Hello, my name is Matthew Newland, and this is part 5 for homework 4. And in this video, we are going to be doing a von Neumann stability analysis for the Crank-Nicolson method for explicit differencing that we used in part 4. So, make this very simple. We're just going to start with what our von Neumann expansion would have been given our previous things we've used back in part 3. So we're just going to start with our von Neumann. So starting from here, we're just going to start with what we got back in part 3 with those two separated sides that we have. So we're going to have t, j, n plus 1, and then in our parentheses, we are going to then start substituting the kind of values we had back in part 3 to what we have in this equation. So it's going to be negative u e I k delta x plus 1 plus 2 u I k delta x plus, oh, that's actually a minus. Let me grab my eraser. Minus u e I k, or that's a negative, excuse me. Negative I k delta x. Then our right side is going to be very, very similar to it, except our signs and our time steps are going to be switched around a little bit. So it's just going to be our temperature at position J, time step N is going to be u e I k delta x plus 1 minus 2 u e I k delta x minus, or no, it's going to be plus e I, or negative, always forget that part, negative I k delta x. So this is our entire von Neumann expansion before we start finding our max term we can find. And the big thing about this von Neumann stability is that we're trying to find why the Crank-Nicolson method does not have an upper bound to it, no matter what value we plug into it. So how do we go from here? So what we want to do is then do kind of a similar situation we had back in our first von Neumann stability analysis, is trying to convert this into cosine and our trig functions using Euler's relationship. So how do we do that? So we have two Euler's relationships here that we can convert, but we're going to divide this side by that side. So we're going to set up a new equation as such. So it's going to be t position j at time point n plus 1 is equal to t, j, n, and then this huge equation now, where we're now going to have a very, very large expansion for what we have. So we're going to immediately convert it with our Euler's relationships. So our Euler's relationships will then have a new relationship as such. It's going to be 2u times cosine k delta x, and then it's going to be plus 1 minus 2u, and then over here it's going to be negative 2u times cosine k delta x plus 1 plus 2u. And then we're going to try to simplify this to get this to a point where we can where we can kind of get it to what we had earlier, where we can just get a max value out of it. So we're going to come over here and say, we're going to come over here. I'm going to sit down first. So we're just going to take this parenthesis down because there's no reason to keep writing these 2 points over and over again. So we're just going to say that we're going to simplify it. So we're going to have, so if we draw out our 1 minus 2u and our 1 plus 2u and also draw a negative sign, we can actually set these two, at least the cosine variables, equal to each other, even though we have that difference with 1 minus 2u and the 1 plus 2u. So we're going to have a new equation as such. It's going to be 1 minus 2u times, should be 1 minus cosine k delta x. That's in parentheses, and then it's going to be over 1 plus 2u, 1 minus cosine k delta x. And then, kind of just to simplify this even farther, we know where our max and min values are because we have that cosine. So our max value for this cosine is going to be 1. So we then can just say that 1, so we're going to convert at least this portion of the equation just to another term. Let's just call it w. So it's going to be w plus w is less than 1. And if you can tell with this, it's like this actually is what we want, because as long as this w value is greater than 0, this will never become greater. This value, or at least the absolute value, this value will never become greater than 1. And that's why this Crank-Nicholson method is very good, even though it's not entirely accurate because we're taking averages and not the actual amount because of our explicit differencing. It still keeps this value under control. So when we're using very, very large time steps, we want to use this average value because this stability will remain as long as we have no matter what we put into it. So with this, that's why we would want to find the Crank-Nicholson von Neumann stability analysis because of that.